OK, so rather than go further into this, I want to turn now to my promised topic to you, to tell you about renormalons. Actually, renormalons have something to do with power correction, so it's not disconnected from what we've been talking about. So what are the ideas here? So we've already seen in our discussion of renormalization that there is a freedom in defining the perturbative series. And we kind of focused on the MS bar scheme as being the simplest thing. But I told you about some subtleties with MS bar, and now we're going to address one of them. It's related to this thing called renormalons. So we have some freedom, if you like, in adjusting the cutoffs. And we had this cutoff mu, and it was dividing up what was perturbative and non-perturbative in MS bar. But we could have done something else. We could have used a different type of cutoff. We could have used a Wilsonian cutoff. And that would have divided up things a little bit differently. And you should ask the question, are there any possible way of dividing things up equivalent? We've already saw when we were doing calculations that for the logarithms, they were equivalent. But it turns out that if you don't, that the powers, sort of the power separation of power divergences can actually have an impact. And that's related to what renormalons are. And MS bar and dim reg basically avoids thinking about power corrections. You just set them to 0. And so what can happen is in MS bar, your matrix elements are having a little bit too much UV physics, and your Wilson coefficients are actually sensitive to the IR. They're not you don't really see it when you look at the coefficient. You just see a number, and it looks pretty good. But there's actually an asymptotic structure to those Wilson coefficients that comes from high orders of perturbation theory. There's things hiding there. That's what this discussion is going to be about. So if you do actually not make a good choice, then it can be the case that when you go to higher orders in the perturbative expansion, you get lousy convergence. And that goes hand in hand, actually, with kind of another thing which is harder to visualize, but I'll explain it. And that is that you have trouble extracting the non-perturbative parameters. And the reason that you're having trouble, so you could think about doing some calculation like that OPE over there, and you extract a value for lambda 1 from all your fits to all these moments I was describing to you. And then you go to one higher order in alpha s, and you extract another value, and all of a sudden this guy changes by a factor of 2, and you wonder what's going on. And you wonder, well, what's nature telling me about the kinetic energy if I change the order of my perturbation theory, and all of a sudden I'm extracting a factor of 2 different value for that matrix element. And that's related, actually, to this poor convergence. These things go hand in hand. That if there's poor convergence in the series, then when you extract matrix elements, you can get different values. Phenomenologically, you can imagine how that would be related. But it's physically related, too. It has to do with the fact that there's a poor convergence here because you haven't divided up the IR physics and the UV physics fully correctly. And that's reflected in this inability to extract these guys in a convergent fashion. And we can actually quantify that using something called Renormalon techniques. So one way of saying it is that if you make a poor choice, you're plagued by something called Renormalons, so they're actually something bad and you don't want them. So what goes wrong is that the short distance coefficients have hidden power law sensitivity to the IR. You wanted these to be UV things, but they're sensitive to the IR. And it comes in dimensional regularization in the powers. We've been very careful about separating out logarithms, but we weren't as careful about powers, and it comes back to haunt us if we look carefully at the theory. And there's a corresponding sensitivity to the UV in the matrix elements. So let me give you an example that's not working through formalism, but just numerics. So let's look at B to U E bar nu at lowest order. The up quark is massless. And we'll think about this like we were talking about for the OPE for charm. We'll think about it inclusively, so we can actually just look at this and it makes physical sense. The same thing that I told you about the charm case applies for the up quark case. The lowest order prediction is just calculate this guy and include loop corrections. The leading power prediction is the same story as for the charm. So that means that physically it's relevant to think about this decay rate. So what does it look like? There's some G Fermi, integrating out the W boson. There's some factors of pi. The mass dimensions of this guy are 1. G Fermi squared is -4, so you need 5 powers. And the thing that's setting the mass dimensions is MB, so you get 5 powers of MB. And if you look at the perturbative series, and you set mu to equal to MB, this is what it looks like. So epsilon, I'm just introducing something which is a counting parameter, and it's 1. I could also make alpha s the counting parameter, but I actually want to stick a number in for alpha s, so alpha s is going to disappear in the next line, and I'll just keep the epsilon, which is just telling me the contribution is coming from this order. So you have some choice here for how you define the B quark mass. Okay, you could use the pole mass, pole in the B quark propagator, or you could use the MS bar mass, or you could use some other definition. And it's raised to the 5th power. So whatever definition you pick it can be pretty sensitive to that. So let me tell you what the results look like in 3 different schemes for that mass. So let's first do the pole scheme. This is the same. We have MB pole to the 5th power. And then we write out what the series looks like in that scheme. You look like you're doing pretty good when you're at 1 loop. You went down by a factor of 5, but then you go to 2 loops and you find that your correction at 2 loops is pretty much the same size as your correction at 1 loop. So you say, well, let's use MS bar. That changes the perturbative series. And maybe you think you're doing a little bit better because at least, well, but this guy got bigger and this guy's bigger than that guy. So it's also not really working. Well, if the phenomenology is as accurate as I told you, you must imagine that there is something that does work better than that. Indeed there is. So there's other mass schemes, and I'll talk about one of them. So continuing this table. Where we switch to something called a 1s mass. Now the series looks like that. We're very happy. Or at least we're much happier than we were over here. So what is the 1s mass? The 1s mass is basically that you take half the perturbative mass for the epsilon system. So the 1s mass is BB bar system calculated perturbatively divided by 2. OK, we'll talk more about why this is working in a minute. Let me also write down the conversion formulas, because you calculate the decay rate once and for all. Say you calculate the first line, then you know how to convert between schemes, and that's what's causing the perturbative series to differ. So MB pole is equal to MB MS bar, and there's a series that relates them. That looks like that. And I could put in numbers here. And so that's what's changing the numbers when I go from this line to this line. And basically, the kind of the five powers of 0.09 that you get takes you from here to here. We could also think about switching from the pole scheme to this MV1S scheme. We have a different series. It still doesn't look very convergent. The numbers look small, but this is supposed to be a 6. But this number here is bigger than that number. But when I stick this series and combine it together with this series for the pole mass, then I get that series at the top of the board. And the problem is not in the MB1S. The problem is in the MB pole. And the problem in the MB pole is being reflected in this series that relates them. And it's poor convergence.
Can you explain what MB perturbative means?
Yeah, so you calculate, so you can think of calculating the Coulomb potential between B and B bar. And that will give you alpha S corrections to just the mass. So you have 2 MB plus Coulomb potential plus radiative corrections to that, and you keep dressing it up and just perturbatively calculate as if it was a Coulomb problem, like QED problem, the mass of the BB bar state. And then you divide by 2.
Doesn't seem that perturbative.
Yeah.
Yeah.
But you just pretend?
There's non-perturbative corrections to it, but what we're extracting from it is the series. OK. I'll explain more why it's going to work, why this is like a reasonable choice, and we'll come to that. OK, so the lesson here is simply that the choice of mass scheme has a big impact on the perturbative series. And we haven't yet figured out why some things work and why some things don't, but we will. And it's absolutely crucial to use the right one, otherwise the predictions will not be good. Well, physically we can actually argue right away why MB pole is not so good. And that's because physically there is no pole. There's no pole in the quark propagator. And that is because of confinement. So we use this notion of pole in a quark propagator when we're doing perturbation theory, but non-perturbatively it's not a well-defined notion, or at least there doesn't really exist poles in quark propagators. So it's only perturbatively a good notion. So I'll say it's only perturbatively meaningful. And in reality is ambiguous. It's an ambiguous notion. And you can think that the amount by which it's ambiguous is related to hadronization, which is set by the scale lambda QCD. So there's an ambiguity in what you mean by a pole mass physically due to non-perturbative effects. Now, when we set up HQET, we actually used M-pole. So we're using a questionable physical parameter. So when we did these phase redefinitions, we were actually using the pole mass scheme because we were expanding about mass shell. So if you were to do other things, you can think about getting to other choices and implementing them in the HQET. No problem with doing that. But there does exist another operator that we sort of dropped without thinking too hard about it. So if we switch to using a different mass scheme, there's some delta M, which you can think of as a series in alpha S, which we wrote on the board a moment ago. And where that delta M would show up is that you would have kind of an L delta M operator, which would just be exactly delta M, and then QV bar QV. That would be left over when we cancel the masses in the Lagrangian, if you like, if you used. It's one way of thinking about it. So we have an extra term in the Lagrangian in HQET. And now you can ask, well, if we have an extra term, we better worry about power counting. And it turns out that the way we can understand why MS bar wasn't working is related to power counting. So in MS bar, if you look at what delta M is, delta M is MB bar itself times alpha. But by power counting, you don't want something that's growing with MB in the Lagrangian. MB bar is suppressed by alpha, so it's alpha at MB. That is providing some suppression, but that's only 0.2. And that's actually just not enough suppression to get rid of the big MB here. You go from 5 GV, there's some number in front, maybe you get down to 1.5, 2 GV, but you're not getting down to a small enough value. So parametrically, this is just not good. Both parametrically because it grows with MB, and numerically, it's too big. It's not order lambda QCD, which would be OK. So parametrically and numerically, delta M is just too big for HQET power counting in this MS bar scheme. You'd include an operator that effectively is, on average, larger and more important than your kinetic term. Because the v dot d operator, v dot d is counting like lambda QCD, and it had v dot d with 2 q's. Now you have something delta m with 2 q's, and this, if it's on average larger, then you're messed up. So that's why actually, physically, the MB bar is not a good choice. You can think about it from the effective theory from that way. MB bar is actually a mass that's, you're supposed to think of it as a mass that you use for high energy physics, for physics really high energy above the B quark mass scale. Then it's a good parameter. We're now doing physics below the B quark mass scale, and this is just one way of seeing why it's not such a good parameter there, because the perturbative corrections are just too big. So what about this 1s mass? So here, it turns out that if you calculate delta m, you get, in the same way that you think about corrections to hydrogen being order alpha squared, you get MB1s alpha squared. And numerically, that's small enough when you put the coefficient in. So it still doesn't make us feel very good because it grows with MB, but if I just care about numerics and I'm doing B quark physics, it works, because the alpha squared is enough suppression that this is a good mass scheme. And that's why the perturbation theory, treating this as order lambda QCD numerically, not parametrically, is okay. Now that, if that doesn't sit pretty with you, you can do something even more fancy, and we'll talk about one example of more fancy a little later on, where you basically, instead of having n show up there, you have some parameter r, and you have something that you can just pick. And so you could pick a scheme here where r is of order lambda QCD by however, maybe you pick it to be 1 GeV or 500 GeV or whatever, 500 MeV or whatever you like. So you can make up a scheme where this is true, and then both parametrically and numerically you're okay. And these schemes also work just as well as the 1s scheme. So we can get more fancy and also satisfy our formal requirement. All right, so that's kind of phenomenological numbers and a bit of physics. Let's come back to some mathematics and talk about what Renormalons are mathematically. Is there a mathematical way of characterizing what's going wrong? What if I didn't think about this physics? Could I do a calculation and see that something's going wrong? And the answer is yes. So first I have to teach you a few things, if you don't know them already, about the asymptotics of perturbative series in quantum field theory. And these are actually not convergent series. So they are what are called asymptotic series. So what's the definition of an asymptotic series? So we'd say a function has an asymptotic series, which is, I'll write as follows, some coefficients, and we'll just call the expansion parameter alpha. You can think of it as alpha s if you like, but this is just math. You don't have to think about it as anything but the expansion parameter. And we say that the function has an asymptotic series if and only if the following is true: f of alpha minus the partial sum up to some level n is less than kind of the scaling that you would get from the next term in the series, which is n plus 2, for some numbers k n plus 2. So that's actually a quite different definition than what you would have for a convergent series. For convergent series, you would say that you could pick any epsilon you like here, and you could make the n big enough that this would get close to that. Here, I'm just saying that it's less than this with some power of alpha. So imagine that I pick alpha to be 0.1. The thing is that this k here could still grow with n. And that actually will happen. So the truncation area, in some sense, is not being bounded in these asymptotic series. And perturbation theory and quantum field theory is generically of this structure, and I'll show you some examples of that. It's asymptotic rather than convergent. So when you do a QFT calculation, kind of typical result, if you work out some asymptotics, is that you would have these Fn coefficients that are some power of a and then times an n factorial. And that's kind of how they're scaling as n is getting large. You can think about the number of diagrams as just growing, but even when diagrams are not growing, you can get these n factorials. So that means if you're fixing alpha as some value of the parameter, and no matter how small you take it, at some order in perturbation theory, you're basically running out of gas, and your truncation error, your predictions start to grow and diverge. So the corresponding values of these k's, that if you had these f's that were of that form, would be that the k's are basically growing in the same way. So you'd need larger and larger numbers in order to satisfy the definition of asymptotic over there. And having these large numbers, you're never able to satisfy convergent. So the series has 0 radius of convergence. And then you wonder, why have we been teaching you quantum field theory? That's true. So what do we know? Even though these series are asymptotic, we can still make use of them. So typically what happens is that the series will decrease. For a while, it'll look like it's convergent, and then it'll start diverging. And you can characterize where it starts to diverge. And I'm not going to go through all the algebra, but I'll just tell you some facts. And so you can imagine that you're doing some perturbation theories, and it looks like it's going well. Things are converging, but then some things don't start to go so well. So think of what I'm plotting here as the partial sum of your perturbation theory at nth order. So I sum up all the corrections up to n. So it's like the series that I was writing over here. It's this thing. Now, in perturbative QED, perturbative QCD, we're never getting more than a few terms. So you could say, well, OK, maybe I don't care so much about this. And in QED, that's actually the case. You don't really care so much about that. But in QCD, actually, the turnover happens already around 3 loops. And so as soon as you start including 2-loop corrections, this is something you have to care about. Now you can say, well, the best thing I can do is stop doing perturbation theory at some n star, because that's kind of where it looks the best, like I've gone towards something, and that actually is not such a bad thing. And it turns out you can characterize actually the mistake you're making by stopping there. And the mistake you're making by stopping there is of the following form. So it's an exponential in 1 over alpha. So you would never be able to see the correction that you need to get to the correct value, which I'm imagining is on the axis here, in perturbation theory, because this doesn't have a perturbative expansion. And I'll actually show you that kind of the bad behavior here and this gap are related to power corrections. And they're exactly related to this connection that I was telling you between perturbative corrections and large order asymptotics and power corrections. This type of exponential is something that we can relate to power corrections, and we'll see how that pans out, although we probably won't get there until next class. Okay, so this is kind of a prelude, and now we're going to go into more detail. And it turns out, in order to go into more detail here, that much as you make Fourier transforms to explore another space, we're going to do a transform to something called Borel space. So it turns out that when you have a divergent series or an asymptotic series, that there's still degrees of divergence. And we can classify how divergent it is by using something called the Borel transform. Yeah.
We use 1S mass. Will the series still be asymptotic?
So no, it's not. Yeah, so 1S mass, let's see. Yeah, it's not, it is still asymptotic, but it's in a way that I'll describe once we understand what this Borel is. It's much less divergent than the other series, than the pole series. If you think about the pole series as being degree 0 divergent, then this is like a few orders down, less divergent. So once we define less divergent of a divergent series, then I'll be able to make that more precise. It's a question of when power corrections come in. And if you look at so physically, the 1S mass is a physical thing for an upsilon state. And if you look at how power corrections come in, then they're suppressed because there's an ambiguity between power corrections and perturbation theory. If the power corrections are suppressed, you have less ambiguity in the perturbation theory. That's another way of thinking about it, about the answer to your question.
That just pushes up n star.
It basically affects this A. All right, lots of good questions. Let's see how we get there. So when I transform, I'm going to call the transform function capital F, and I'm going to call its argument B for Borel. And so what's the definition of the Borel transform? We're going to define it as follows. There's a first order term, and I'm just going to put a delta function there. The real thing that matters is the series of terms that come next. And instead of having f to the n, alpha to the n, I'm going to divide by an extra n factorial. And that's the definition of, given a set of f's, how I construct what's called the Borel transform. And because of the n factorial, I get improved convergence. So the n factorial is making it converge better. So if there's a transform, there should be an inverse transform. So here's the inverse transform. It's an integral from 0 to infinity, b over alpha f of b. And that would get me back to the f. So if you have a convergence series, and you think of this transform, then you just can go back and forth, and you get back the function that you started with. So if you have some series that's like that, you get back. You could calculate that series, and you get some f of alpha just before Borel transforming. If you do this Borel transform, then you calculate this integral, you get back the same f of alpha from the inverse transform. Let me give you an example that shows you that if you have a divergence series, it's not too crazy to define the sum of the divergence series by using these transforms. So I claim that for a divergence series where f of b and the inverse transform exist, so if we start with the divergence series, but these things exist, then we could just use this transform as a way of defining f of alpha. So let me give you a simple example of that, convince you that it's not such a bad thing to do. So let's consider the following series. Just an alternating series, but alpha is a parameter greater than 1. That series doesn't converge. Of course, for alpha less than 1, it would converge. And if I asked you what it should be, you would say, well, I calculate for alpha less than 1 and I analytically continue, and it's alpha over 1 plus alpha. Well, that's one way of getting there. Another way of getting there is using this Borel transform. So if you calculate it here, f of b, you sum up 0 to infinity, minus b to the n. Once you put the minus 1 in there, and there's an extra n factorial. So that's e to the minus b, perfectly well-behaved function. And then you have to do an integral, 0 to infinity db. You have e to the minus b over alpha times the f of b, which is e to the minus b. And that just gives you alpha over 1 plus alpha. And this is a perfectly well-defined integral for large alpha. Large alpha is even making it better. So the integral is perfectly well-defined, and we get an answer that we like. Okay, so this Borel transform is a useful way of dealing with divergent series. The real question is what happens if the inverse transform doesn't exist. And that's what's going to be the thing that we're most interested in. So the f of b integral over the f of b doesn't exist. Then the integrand can tell us about the severity of the singularities. i.e. the severity of the divergence. And that's the real power of this Borel method. So let's do another example where I actually think will diverge. So let me take fn to be a to the minus n plus k factorial. Then if we do the Borel transform of that, do the series, you can do it. And there's only one piece of it that we care about, so I'm just going to write that piece. So there's this piece that has a kind of pole-like structure. And it has a pole at b equals a. And what you say is you call this pole a renormalon. This is the renormalon. You call it a b equals a renormalon. So you're characterizing the renormalon by where that pole is. Renormalon is the flavor of a particle. This has nothing to do with a particle. Usually you think of poles as having something to do with particles, and that's where the name comes from. Studie te Hoof, blame him. So if A is less than 0, your integration contour is positive, and the pole is on the other side, so you don't have a problem. The inverse transform exists. These are called UV renormalons. They still can guide the perturbation theory, and they can be important for sort of thinking about why the perturbation theory is behaving the way it is, but you can do the inverse transform. The real ones that are kind of problematic are A greater than 0, because then the pole is on the integration contour, and we can't do the transform. So we're integrating dB from 0 to infinity, and we just have a pole sitting on the axis, and what do we do? So you could think about characterizing how poorly behaved a perturbation theory is by looking at these poles. And that's kind of what I meant by having some kind of notion of how divergent a series is. So you look in this Borel space, and you look at the real axis, and there's poles actually can be both on both sides. The most severe pole is the one that's closest to the origin. And that has the smallest value of b. And you can see if you have a small value of b, then you're multiplying here with some large numbers. So if a was 0.1, you'd be multiplying by 10 to the n. So these guys are more severe. As you go to larger values, you get additional suppression from this a to the n. So if you went all the way out to 100, then you'd have a 1 over 100 to the n. That's good, but factorial eventually wins. So it's still divergent, but we look like it was a lot better. Okay, so you can characterize how severe the series is diverging by the location of these poles. And you can characterize the ambiguity in doing an integration by, if you just think about one pole, you can characterize the ambiguity. So let's just imagine there's one pole. You can characterize the ambiguity by going above or below. So two possible ways of defining the integral. You don't know which to pick. One is to go above. The other is to go below. And then you can think about what the ambiguity is. And the ambiguity is the contour 1. I'll call this C1, this is C2. The ambiguity is C1 minus C2, and that is circling the pole. So you can look at the residue of the pole, and that gives you the ambiguity. So what we'll do next time is we'll look at an example in perturbative QCD. We'll see that there's a series that has a renormalon, and we'll find it, and then we'll look at the residue, and we'll find actually that it will get out will pop lambda QCD. So we'll calculate for some perturbative series that the pole mass really has an ambiguity of order lambda QCD by using this technique of going around a residue of a pole.
So
Okay.
When we say that the B quark is a 4 GeV mass, what's that mass?
Yeah, so if you say that B quark has like 4.2 GeV mass, that's the MS bar mass. If you say it has a 4.73 GeV mass, that's like the MB1S mass. And if you look at how the PDG measures the B quark mass, they measure it in one of these schemes that I'm telling you about, like the 1S scheme. They quote a result for that. You can convert between the 1S and the MS bar mass. The MS bar mass is a perfectly well-defined quantity. It doesn't actually have a renormalon, okay? That's not its problem. The pole mass has a renormalon. The MS bar mass, its problem is related to power counting in the low energy theory. It's a good mass for high energy physics. It's a bad mass for low energy physics. That's the problem with MS bar. It's not a technical problem that it has severity of Renormalon. It can have a higher order Renormalon, but it doesn't have the same severity of Renormalon as the pole mass. The pole mass basically has the most severe possible Renormalon, which is in some units a half. So there's an extra 2 to the n. We'll talk about that next time. So basically, it's the U equals a half Renormalons that really are causing a problem in perturbative QC. They're the most important. There's higher order ones. Even alpha S actually has a Renormalon, alpha S in the MS bar scheme, I suspect. but even up to 5 loops, you won't see it, or it's very hard to see. Let's stop there.